Okay, so let's begin. So just want to remark that practitioners who structure financial products often speak loosely about adding optionality to a simpler financial product, and that to a mathematician, addition is a binary operation. So a binary operation is actually formally defined by mathematicians as a way of combining two numbers in the same set to produce a third number in that set. And addition certainly does that for real numbers, say, but mathematicians don't require binary operations to be restricted to familiar ones such as addition and multiplication. So multiplication is, however, a binary operation, and it's related to addition in at least two ways. So multiplication distributes over addition, and multiplication is isomorphic to addition. So isomorphic means like that there exists a structure preserving map between the numbers in this case. And things like addition is commutative and associative and has a neutral element and has an inverse, and multiplication would have all those things as well. So there's an isomorphism. So the talk is going to consider the possibility of a third binary operation. And because all of you are in finance, that third binary operation is going to capture the optionality that practitioners speak loosely about. So here's an overview of the talk. And first, review financial applications of multiplication and addition. And as I said, multiplication distributes over addition, but it's natural to ask, what does addition distribute over, if anything? We introduced a third binary operation. It's naturally called either log add or option. And I always thought it amusing that though in multiplication, you see the same ending as in option. In addition, you see the same ending as an option. And even in binary operation, you have option embedded inside it. So ordinary addition does distribute over this binary operation I'm calling option. And so we're going to consider the valuation of a married put. So in case you've forgotten, a married put is a portfolio which combines a vanilla put with its underlying asset. And so we'll be interested in the valuation of a married put, and you can use these valuations to value calls and puts as a result. And the married put pays off the larger of the strike price of the put and the underlying security, its price today. And it pays off when it matures, the larger of the strike price and the underlying security price then. And we'll want to value this married put, and we'll do so by thinking of it as combining the strike price with the underlying security price today. And this way of combining the two numbers is going to be a binary operation, so it keeps the numbers in the same set. And we'll call this binary operation option. So we're going to introduce a new financial product called a stoption. That's what's in the title. It arises by repeatedly optioning. And stoptions have a Bermudian exercise style, and yet are amenable to closed form valuation. And okay, I wrote in a particular arbitrage tree model, and that's what we'll focus on. But actually, I've looked at valuing these stoptions in the Black-Scholes model, and there's a closed form valuation formula there as well. So it's more a feature of the contract rather than the model. So the results are suggesting that abstract algebra has potentially important implications for understanding early exercise of derivative securities. And although I'll be focused on Bermudian exercise, one can also think about these things for American exercise. So, okay, so let's just review some things that are very familiar to all of you at first. And so we want to consider the product of two non-negative numbers. We call them G1 and G2. And the product has several financial interpretations. So for example, if you had a long position in G1 shares of a stock worth G2 per share, the value of the position is just the ordinary product of the number of shares and the price per share. A different financial interpretation. So I'll remind you that a gross return, if there's no dividends, is just a price ratio. And so consider gross returns over two successive periods, two adjacent periods. So let the two gross returns be G1 and G2. And if you multiply the gross returns, then you're getting the gross return over the entire two periods mashed together. And so there's a second financial interpretation of ordinary multiplication. I'm sure there's more. So in high school, I learned about logarithms, and I learned that multiplying two positive numbers can be reduced to adding two real numbers by taking logs. So you remember this by saying the log of a product is the sum of the logs, and mathematically it's indicated in this third bullet point. And so we can sort of transition, if you will, from ordinary multiplication to ordinary addition by taking logs. And you can also financially interpret addition. So for example, A1 plus A2, where A1 and A2 are both real numbers, is the value of a bond paying A1 in one period and A2 in the second period, if there's no interest rates, so zero interest rates. And different financial interpretation of A1 plus A2 is that it's the non-annualized log price relative over two periods, where A1 is the log price relative over the first period and A2 is the log price relative over the second period. So, okay, so we've seen that we can transition from multiplication to addition by taking logs, and that whether we are trying to interpret the multiplication of two numbers or the addition of two numbers, we can provide financial interpretations easily. So I used natural log to do the transition from multiplication to addition, but actually you can use the log for any base. So let's say I use the base e to the 1 over b. Then if you kind of try and remember your high school introduction to logs, you'll soon appreciate that you can convert from multiplication to addition using, let's say, any base, or equivalently b times the natural log. Okay, so the natural log is base e, and if you just multiply by that base e log by a positive quantity b, then you still are converting multiplication to addition. Okay, so so the mathematician would say that you're converting multiplication to addition using a generator, which is the positive quantity b times the natural log. And there are other generators that could be applied to multiplication to get something other than ordinary addition. But we're going to ask a different question. We're going to ask what happens if we apply this exact same generator, which is b log, to addition. Okay, so this actually comes up a lot, it seems, in finance, this sort of addition of exponentials. How many times have you told students that the sum of two log normals is not log normal? So anyway, we kind of have an answer to the sum of exponentials of here non-random things. And just as a matter of definition, we're defining a third binary operation, which is denoted by circle plus subscript L superscript B by the right-hand side of this equation. And what's happening is we're starting with two numbers, A1 and A2, both real. And then for any fixed B, there's a unique map we're applying to both of those numbers, which is to divide each number by B and then exponentiate. So having applied that map to the two numbers, we have the numbers e to the A1 over B and then e to the A2 over B. And then we combine them using ordinary addition, and then we reverse that map. So the inverse of the original map, which was divide by B and exponentiate, the inverse of that map is to take the natural log and multiply by B. So that's what we're doing to define this third binary operation. And so we can call the right-hand side the log sum exponential. But the question arises, can we actually also financially interpret this third binary operation as we were able to financially interpret multiplication and addition? So the answer will be yes. And I want to introduce or remind you about a married put. And we're going to be thinking of it as written on a real valued underlying security. So the price of the underlying can go negative. So it's not a stock, but it could be a value of a swap, for example. And so little s here with a subscript capital T is a random real valued price at a future date of some security. Notice I didn't say asset, I said security, so it can go negative in value. And it'll be non-dividend paying for simplicity. And the price today is some real value S0. And I'll just remind you that a vanilla put written on this real valued underlying could be a crude oil futures price, for example. It has some strike, which in general is real, maturing at some future date, has a payoff of 0, maxed with the strike A1 less the price of the underlying little s. So married put, which is also called covered put, is a static portfolio consisting of one vanilla put with that payoff and one share of its underlying security. Okay, so one unit of its underlying security. So the underlying security at maturity of the vanilla put is worth a little less. And if you literally, combine by ordinary addition, the payoff of the vanilla put, which is highlighted here, with the payoff from its underlying, then the payoff simplifies to that, the larger of the strike and the underlying security price and maturity. And that max that's between A1 and the random security price and maturity, that max is actually a binary operation. If A1 and little s are both real, then the max of the two is also real, and that's all you need to be called a binary operation. But the max also has a lot of other properties that we like binary operations to have. So for example, it's commutative, it's associative, and it even has a neutral element, which is turns out to be minus infinity. So over the set of reals. And when you extend the reals to include minus infinity. So, okay, so so yet another nice property is that ordinary addition distributes over this max. So in your mind's eye, if you were to ordinary add, say on the right, some real number A2, you would to the max, it would be the same as first adding A1 with A2, second adding S with A2, and then taking the max. Okay, so we're going to assume zero interest rates throughout this talk for simplicity. You can always bring in deterministic interest rates with no difficulty and work with forward prices. And so we're going to assume no arbitrage. And that means from the first fundamental theorem of asset pricing, the existence of a risk neutral probability measure. I'll call it Q as usual, but we're going to subscript it L. Why? Because we're going to be thinking about a particular risk neutral probability measure. And it's the subscript L is arising because we're going to think of the underlying security price, which again is a real valued random quantity at maturity. We're going to think of that as having a logistic distribution in particular. So you may or may not be familiar with the logistic distribution. It's qualitatively similar to a normal distribution in that it's unimodal, it's fully described by two parameters. One of the parameters is the mean. The other parameter is not actually the standard deviation when it's written in the usual form. So the second parameter that along with the mean fully determines the logistic distribution is typically called scale parameter. So it controls the scale of the random variable. And so if you start with a standard logistic with scale 1 and then multiply by a quantity B, you'll get a logistic distribution with scale B. So that's the origin of the name. And so the cumulative distribution function of the logistic distribution is available in closed form, which is actually not true for a normal random variable. I mean, all we do there is let's say define the integral of the Gaussian as a special function, but let's say we cannot actually do that integral in terms of elementary functions. So in contrast, the cumulative distribution function of logistic is actually expressed as an elementary function, and it's right here in the second bullet point. So the probability that a logistically distributed random variable S is less than some threshold A1, and we can do it conditional on the mean being some number A2, is given by the quantity on the right. And that's a fairly simple expression, obviously not involving any integrals. And but we could differentiate that to get the density, no problem. And as an aside, there's abstract algebra can be used to analyze the density of logistic as well, but we won't go there. So the scale parameter, we're going to call it bewilderment. So it's similar in concept to volatility, but let's say we think of a volatility as well. So it is, in that both a volatility and bewilderment are greater than 0. But let's say volatility in finance usually means something like standard deviation, often of log of a positive asset price. And let's say I'm not tying myself to the concept of standard deviation per se. There are other measures of spread of a distribution. Mean interquartile range comes to mind, and bewilderment is yet another measure of spread, but it's not literally equal to standard deviation. The only difference is that there's a positive constant other than 1 between a standard deviation and bewilderment, but we'll be working with bewilderment. Okay, so the interesting thing about assuming a logistically distributed underlying is that when you value a married put, you get a nice simple formula for the value today, and it's written here at the bottom of this slide, and it's a log sum exponential of the strike A1 of the vanilla put and the married put, and the value A2 of the underlying security price today. Okay, so that's, let's say why we're interested in this logistic distribution in this talk about applying abstract algebra to derivatives pricing. And so we're going to be thinking of this formula as actually a binary operation that is being applied to the strike A1 and the current price of the underlying A2. And so just a quick reminder that if you started with ordinary multiplication and wanted to instead think about ordinary addition, then a positive constant b times natural log is the generator that lets you do that transformation from multiplication to addition. And if you are at addition and you apply the same generator to addition now, you get this equation at the bottom, and it's actually financially interpreted as the value of a married put struck at A1 and whose underlying is at A2. Okay, so this binary operation that we're using to value a married put in a particular model, it has certain properties. So it's commutative. So the order in which you, like if the strike were, say, let's just pick some numbers. If the strike were, say, -2, which is a number we allow, and the underlying were at, say, 3, another number we allow, then if I were to change it so that the strike was actually 3 and the underlying was at -2, we would have got the same value for the married put in this model. Okay, so the binary operation is also associative. So the associativity you can think of as coming from the associativity of ordinary addition. Like if you look up here where I've highlighted or the ordinary plus, what we're doing is again, we're starting with numbers A1 and A2, which are real, mapping them to a pair of positive reals via the exponential function, then adding those positive reals. And of course, the sum of two positive reals is a positive real. So that's the closure property that defines a binary operation. And then we undo that map by taking b log, taking us back to real numbers. So, okay, so if you recall, associativity actually involves three numbers. And a way of saying it is that brackets don't matter. And for ordinary addition, we know brackets don't matter. Okay, so it turns out if you want a binary operation to be associative, then you need a generator, which is an invertible function, to exist between that binary operation and ordinary addition. And here we see that the generator is b log. So, so when you have an algebraic structure that has a single binary operation, which is commutative and associative, then the name people in abstract algebra give to that algebraic structure is a commutative semigroup. So semigroups, by the way, are widely used in probability theory, as you may know, especially for Markov processes. And so we're using semigroups in a different way to think about option valuation. And actually, we can add more structure to the semigroup and still apply them to valuing options. So we want to, make clear that for this new binary operation, circle plus, which is logarithm exponential, there is a so-called neutral element or null element, goes by either name, and it's minus infinity. So the reason this deserves the name of null element is that when you make one of the two numbers be this minus infinity, then you get the other number back. And so saying it financially, if you had a married put, but strike was actually minus infinity, then that's just like having the underlying, because you would never, choose minus infinity over the real value of the underlying. Okay, at maturity. So the set we're now formally working over, if we want to include minus infinity in the set, is going to be denoted by the real line with a subscript minus infinity. And when we think of a binary operation over that slightly larger set, including minus infinity, which is associative and commutative and has the neutral element of minus infinity, that's called a commutative monoid. So monoid is the term when there's a single binary operation. And you may have possibly heard of the term group in this setting as well. So for group, there's an additional axiom that needs to be satisfied. And let's say over this set of real numbers, including minus infinity, that additional axiom is not satisfied. So this is sort of as far as we can go over this set. It does turn out if we extend the set to the complex plane, we can talk about groups, but we're not going to go do that right now. So the okay, so the key thing is that this algebraic structure with a single binary operation called, let's say, log sum exponential, or also called option, it has the property that ordinary addition distributes over the option valuation binary operation. So you can now think of an algebraic structure with two binary operations, this one and that one. And believe it or not, like there is this algebraic structure, which is called a semifield, is like isomorphic to a very familiar algebraic structure to people in finance. That's on the next bullet point, which I want to go through carefully. So, okay, so the view here is that this option binary operation, we'll think of it as, quote, a new addition. Okay, so there is an actual mathematical sense in why we can call this addition. And it's not literally ordinary addition, but it has many of the properties that ordinary addition has. And so the other part of the view is that ordinary addition is, believe it or not, our new multiplication. Okay, so why do we call ordinary addition multiplication? Is it just to be difficult? No, it's because this ordinary plus that I've highlighted distributes over this new addition, and just as ordinary multiplication distributes over ordinary addition. So in this algebraic structure that I'm calling a semifield, the You can log add, which is the first binary operation. You can log multiply, which you know as ordinary addition. And you can also log divide, which you know as ordinary subtraction. But unfortunately, you can't necessarily log subtract. Okay, so if I asked, what's the kind of inverse binary operation to that one, let's say we can name it log subtraction, but it turns out if we want to stay in the set we're in, which is real numbers including minus infinity, you can only work with log subtracting a smaller number from a bigger one. And let's say that means that you can't arbitrarily log subtract any two real numbers. Okay, so so anyways, so let's say why we call this a semi-field and not a field, and because of the restriction, let's say, on the inverse of this, that it doesn't, it's not necessarily, this inverse operation is not necessarily there. And so anyway, so this algebraic structure we find ourselves working in when thinking about valuing married puts, it's actually isomorphic to an algebraic structure that people in finance use a lot. Okay, so if all you do is say, I just want to be able to ordinary add and ordinary multiply, but I only want to consider non-negative real numbers, okay, then it turns out the algebraic structure you're working in is called a semi-field. So a concrete example is in corporate finance, and we have an equation like assets equals debt plus owner's equity. Okay, and there we're actually thinking of assets as non-negative, debt as non-negative, and owner's equity as non-negative. And there's no issues if we wanted to subtract a smaller number from a bigger number. So we might say, for example, that if the assets are 3 and the debt is 2, that the owner's equity is 1. But what we don't ever wish to consider is when the assets are 2 and the debt is 3. And then, to say that therefore 2 minus 3 is minus 1, because we're leaving the set of non-negative reals. So let's say we unwittingly find ourselves in this algebraic structure all the time in finance. And, I'm saying that if you take as a generator the log for any base, not necessarily base E, then you actually end up in this isomorphic semi-field. And let's say the choice of base is controlled by this superscript B, which will play the role of volatility, well, not literally equal to it. Okay, so so having understood that that there's a binary operation between, let's say, a strike price and underlying security price that gives us a married put value in this logistic model that's arbitrage free. This married put value is arbitrage free. And we can ask, well, what about, repeatedly applying this binary operation? So before we do that, let's just review repeated ordinary multiplication and repeated ordinary addition. So consider, n positive reals. We can multiply them with each other arbitrarily, let's say, and interpret the repeated multiplication financially. So one interpretation is that each GI is the gross return in a period I, so the random numbers, and that the product is the gross return over the I'm not sure why I wrote n plus 1 periods. It should have been n periods, so there's a typo there. Okay, over the n periods. And so the and now if we just take logs of gross returns, we get log price relatives. And so if we simply apply as a generator b times natural log, which you can be thinking of as log for a base e to the 1 over b, then you're converting the multiplication of gross returns into the addition of log price relatives, which is something I know you're incredibly familiar with. And so that's one interpretation of a repeated sum. But a second interpretation financially of a repeated sum is that you have n future cash flows, A1, A2 to AN, from a bond. These are real cash flows. And then if they had zero interest rates, I want to value the bond, I would just sum the cash flows, assuming no default. So, okay, so we've seen financial interpretations of repeated multiplication, repeated ordinary multiplication, repeated ordinary addition. What about repeated optionality? So, okay, so a reminder that just a married put involves a single application of the optionality binary operation between, let's say, two numbers, which I'm writing here as A0 and A1. Can we financially interpret doing this binary operation, two or more times? So the answer will be yes, and we'll be led to a contract called a stoption that's in the title of this talk. So I want to first remind you how futures contracts work, because a stoption will be very similar. So to enter into a futures contract, you enter at zero cost, you mark to market every business day. Let capital F subscript I be the futures price at the close of business day I. So if you're long one futures contract, then you're going to pay this price change to the party you short every business day, and the highlighted quantity can be positive or negative. So we're going to continue to assume zero interest rates. And so under zero rates, if you have a futures contract alive for n days, then the marking to market proceeds will sort of telescope, and you'll get just final futures price minus initial. An example of futures price that can be negative is, say, crude oil futures. And so we're going to be thinking about the futures price as possibly negative, and of course price increments are always possibly negative, but we're going to think of the most negative value of futures price increment as minus infinity. So in this world where futures prices can be arbitrarily negative, then the marking to market can also be arbitrarily negative. And obviously, if you're long one futures contract, you're not happy about very negative futures price changes. And so we are going to introduce the notion of a stoption. So what is a stoption? Well, it differs from a standard futures contract in that there's some upfront premium. Whereas for a futures contract, the premium is always zero. And so if you're going to pay this premium, perhaps you want something back, and you're going to get something back from the stoption. So what you're going to get back is the right to swap any of the n marking to market proceeds. And when you swap one of them, you replace that realized value, which is possibly negative, for a number which is also real but is not random. It's known at time zero. And these numbers, there's a typo there. It should be A1, A2 to AN, sorry. So anyways, these numbers are, we'll call them floors. So an example is that, say, a floor is zero, and then you swap a negative price change for zero. So that's a good thing. So you're happy to be able to do that. And so the way this contract is formally written is that you have to exchange one of these futures price increments. Okay, now that said, you could say, Carr, why are you calling this a stoption? And it's more like some kind of forward contract, but let's say with multiple dates of exercise. And there's some truth to that statement, but let me defend myself for calling this a stoption in two different ways. So first, you do have optionality over when you have to do this swap. So there's timing optionality, we'll say. And then second, it turns out that, say I made a n there, the final floor, say I made that minus infinity. And moreover, I thought of the contract as written on the n minus 1 price changes rather than the n price changes we're currently thinking about. Then it turns out that you can think of it as that you're not forced to exercise one of the n-1 price changes. And, let's say, and when the final floor is written here, an is minus infinity, that's like equivalent, okay? So to not being forced to exercise at all. So you might have to think about that. But so anyway, so I'm going to stay with this term stoption. And again, I feel like I've defended it two different ways. So it's a reasonable term. But for your first cut through this, I suggest you just think of it as you're being forced to exercise once. The optionality is merely about timing. So, okay, so there's a Bermudan option clearly in this contract, like the opportunities to exercise or not are at the end of each of n days. So how do we determine the upfront premium? And okay, so we're going to use dynamic programming. Like we're going to be in this logistic model, and I'll tell you exactly what that model is in a moment. But I'll just say right now, the futures price process in this model is Markovian, and so dynamic programming is applicable. And okay, so it'll be important to have the notion of a value function to apply dynamic programming, and v here will be the value function. It's subscripted I for the time that you're thinking about in the future, and it's superscripted j in brackets for the number of remaining exercise opportunities. So I don't actually need that superscript, but it's just a helpful reminder. If you know I, you know j. J is n minus I, but I just prefer to have it there. And okay, so Vij is the value of the stoption, conditional on not stopping prior, okay, and but having the ability to stop after. And j is the number of times you can stop after. And so we're going to use dynamic programming, recursing backwards for maturity. And the model we're in is going to say that under risk neutral measure, all futures price increments are independently identically distributed with a logistic distribution, mean zero, so that they're risk neutral, and they have a common scale parameter b. Okay, so this is somewhat analogous to the Bachelier model, but the distribution we're using for price changes is not normal, but logistic. And as a result, let's say the parameter controlling the width is not a standard deviation, but rather the so-called scale parameter of a logistic, which is just a positive multiple of standard deviation. Okay, so we're going to actually start this dynamic programming exercise one period before maturity as opposed to at maturity. And so you have this stoption, and you've probably forgotten what the payoffs are, but basically the way to think about it is you can swap a future price change for a constant, and you have to swap one of them. So if you put yourself one period before maturity, then there's only one remaining futures price change, which is Fn minus 1, and you basically have to swap that for An. So, recall we conditioned on not exercising prior. So you would have accumulated all the previously unswapped price changes, which telescoped into what's highlighted. And then because you're forced to swap the last price change for An, we add that. Okay, so this is how we come to this formula on the right, and we'll sort of start from here. So we back up one period, and now you're at time n minus 2, and you have the ability to swap the Fn minus 2 minus Fn minus 1 price change for An minus 1. And so if you did that, we would add this An minus 1 to all the previously unswapped price changes. And but you don't have to exercise the time n minus 1. You could continue. And if you continue, you get the continuation value, which is in the bullet point above. So obviously you're going to choose the larger of the stopping value at n minus 1 and the continuation value at n minus 1. So the max appears. So we're just going to do some algebra. So we're going to substitute in this right there, and that leads to this. And now we're going to take advantage of the distributivity of ordinary addition over the max and over the expectation. So so I'm going to pull out, if you will, this fn minus 2 minus f0 from both of the maximans. So it's kind of implicit in there. And so after you, quote, pull it out, this is what you're left with. And what you're actually left with, if you think about it, is a single period stoption. So you can think of the world ending at time n minus 1, and you can have, you know, the floor an minus 1, or you can have a random quantity, and you're going to choose the larger. So this expectation is something we've thought about. So it was when we first considering, you know, what the circle plus binary operation is, we said it was a married put, and this is a married put calculation because we're at time n minus 2, and if you will, that's random, but everything else is deterministic. So we know how to value it, and this is how we value the married put, and so we stick that in. So okay, so now we're ready to step back one more period. Before we do, let's just record what the continuation value was at n minus 2. So we step back to time n minus 3. We sort of turn the crank. We want the conditional expectation of stopping at time n minus 2 or continuing. We plug in the continuation value. We can again factor out. And okay, now what we're having to do over here, it still is a married put calculation. We're at time n minus 3. The only thing random is this futures price at n minus 2. So we can apply our married put valuation formula, and because it's associative, we can actually drop brackets. So here's where we are, and I'll just summarize what the values were at times of the continuation value at times n minus 1, n minus 2, n minus 3. Okay, and if you're a poor mathematician like me, you'll just guess the answer, and so you'll say the answer at time 0 is this as your guess, and you can formally prove that that's a good guess. So, okay, so we financially interpreted the repeated option as the upfront premium of a stoption. So this is a very simple closed form formula for this contract. If we had switched the model to, say, the Bachelier model, we would actually have a fairly similar formula to this one. Well, the one difference would be that in the Bachelier model, the binary operation is not associative. So you would require n minus 1 brackets in the highlighted expression, and you would have a different binary operation than the log sum exponential if you were using the Bachelier model. But those would be the only differences. Okay, so you would be putting in brackets in the Bachelier model between an minus 1 and an, and then you'd need another bracket just before the an minus 2, and you'd need brackets before every one of the a's, is a way of saying it, except the last one, I guess. And okay, so that's n minus 1 brackets, and then you would actually have valued this contract in the Bachelier model in closed form. And to be honest, like the the fact that you have to do the binary operations in a particular order in the Bachelier model, whereas you're sort of free to choose the order in the logistic model, is not a huge, let's say a huge consideration from computational perspective. So it takes just as long to do the binary operations in a particular order as in no particular order. So let's say, maybe the most interesting thing is the stoption contract as opposed to the model we happen to be using to value them in now. So in the model we're in now, the logistic model, I could like change the order in which you see those floors arbitrarily and not change the value. Okay, so if, for example, A1 was 1, A2 was 2, and AN was n, and then I switched it so that A1 was n, A2 was n minus 1, and A1 was 1, it wouldn't matter for the value in the logistic model, whereas it would value in the Bachelier model. Okay, so let's do some examples, and say it's a 2-day stoption. We're going to be monitoring daily, and the general formula, let's say, is reminder is here. So if it's a 2-day stoption, then you end up, so the payoffs are what? Well, you have to exercise either time 1 or time 2. If you exercise at time 1, you have to swap the first price change for A1, and so the payoff is just A1 if you exercise at time 1. And if instead you exercise at time 2, then since you didn't exercise at time 1, at time 2 you're getting the first day's price change, okay, plus the second day's floor. And so anyway, so when you take you'll choose the larger of those two at time 1, and then when you take the expected value, you end up with this, okay, the log sum exponential of the two floors, A1 and A2. And let's illustrate that with numbers. So say this parameter B, which just needed to be positive, happened to be 1/2, and say that the two floors, which just need to be real, are log 3 and log 4, which happen to be positive numbers, but they didn't need to be. Then the 2-day stoption value turns out to be log 5. Okay, and implicitly a Pythagorean triple was used there, and so we're kind of taking the log of the 3, 4, 5 Pythagorean triple that you are familiar with from high school. And we could also illustrate with a 3-day stoption. So you have to exercise at time 1 or time 2 or time 3. And the 3 floors, let's say that they're log 3, log 4, and you probably expect me to say log 5, but I'm actually going to say log 12. And anyway, we'll keep this scale parameter B at 1/2 like it was in the previous example, and use the formula to calculate the 3-day stoption value. Now I put brackets in this expression, but they weren't needed. But anyway, if I did choose to first do things in this order, like I would have taken, the pseudo sum of log 3 and log 4, which from the previous slide is log 5, and then you have to combine it with log 12. And you might remember that 5, 12, 13 is a Pythagorean triple, and that the log 5 pseudo added to log 12 is log 13. And so you can kind of see the value, no pun intended, of having an associative binary operation, because we could take the previously calculated 2-day stoption value and just sort of extend the maturity by 1 period, and we didn't have to sort of recalculate these values. Having already calculated them once, we can just use that calculation. And so we obviously, fairly obviously, we add optionality if we extend the maturity. The value should go up, and it certainly does, from log 5 to log 13. And all we had to do to capture the increase in value is pseudo add log 12 to the existing log 5 value. Okay, so just more generally, there's n floors, and I'm running out of time. You can sort of a natural value to set all the floors is 0, and then in that case, the formula simplifies to that. And so so in this model, if you're asking yourself, how do at the money stoption values increase with maturity, the answer is they grow with the log, as the log of the maturity. And let's say the spirit is that we're adding in quotes a set of numbers, so that's called a series. And we could have, for example, made the floors be a geometric series, for example, and used the well-known formula for a geometric series in our context. So you can sort of further simplify these formulas for special structure on the floors. And so that's something to keep in mind. So it's a Bermudan stoption. And so one is naturally interested in, when should I optimally exercise early? So it turns out, I'm not going to go through this slide in detail, but I just say that you can calculate exactly when you're supposed to optimally exercise early. Very explicit formulas for everything. And then the next point is that the theory of derivative pricing was based on replication. So far, let's say, I've not talked about replication. It turns out you can replicate, and moreover, it's the fact that algebraic structure is being used that causes the ability to replicate. So there's a replication strategy in this discrete time model, and the replication strategy has you roll over a portfolio of riskless asset and one-day vanilla calls when you're monitoring daily. And it's the fact that, it's the fact that, let me just show you in the case of the 3-day stoption. So the 3-day stoption value is this, that's the target, but you can think of it as a 2-day stoption, which is got a strike of what's highlighted. And it turns out a 2-day stoption is very closely related to a 1-day call. So it's that fact that's allowing the replication. Okay. All right, let me just wrap up. So we presented the logistic model of option pricing and showed that the value of a married put is the log sum, or if you want to call it option, between the initial security value and the strike price. And a repeated sum is just a sum of sums, which you already knew. But likewise, a repeated option, so an option on an option, is just the value of a Bermudan option that's embedded in a stoption. And so that's the big virtue, I'd say, of this algebraic point of view. It's to, finally get some analytic understanding of early exercise. And, we're not yet at the level where one can value a garden variety Bermudan swaption or an American option on a stock, but let's say we're getting closer. And so the, everything is explicit for this stoption in this model. And you can also, you might have noted that the whole presentation was in discrete time, and wonder, is there a supporting continuous time model? So the good news is that there is. I just published a paper with a co-author, Lorenzo Torricelli, in Finance and Stochastic that gives the supporting continuous time dynamics for this logistic model and for another model. In this other model, the underlying security price is non-negative as opposed to real valued. So if you were bothered by the fact that security prices in this presentation could go negative, don't worry. There is a whole parallel existing structure. It's actually isomorphic to everything you've seen here that allows security prices to be non-negative. And in that isomorphic structure, the stoption is written on price ratios rather than price differences. Okay, so if you found this interesting and want to learn more, you can pull out your phone and take a snapshot of this QR code, and it will take you to my webpage where you'll find a paper that has infinitely more detail than we've been able to cover in this 55-minute talk. Okay, that's it for me. I wanted to try and leave time for questions or comments. So I'm done. I'm going to stop share and see if there's anything in chat. And
so there are no
okay,
questions in the chat, but at this point, if anyone wants to ask a question, feel free to unmute yourself and use your microphone.
Okay, well, not hearing any questions. Just say I'm giving a similar talk this evening, 9 p.m. And if you're really a glutton for punishment, you can tune into that one. Just ask me for the Zoom link. And I'll be covering the sort of positive analog of everything we saw today. It's actually slightly more complicated. So I didn't do it today, but let's say they both have their uses. And so I just let you know that that's happening.
So is there an application of a swaption in practice? I'll tell you what I'm thinking about.
Go ahead.
So you have an OTC derivatives contract, like a swap, that could have a negative value.
Mm-hmm.
And you've posted collateral, maybe A1, A2, A3 could be the collateral amounts. Maybe they're all equal to each other. And then once you have the right to not top up the collateral if the mark to market exceeds the collateral.
Okay, I mean, that was just a brilliant insight, Neil. So yes, that's actually described in the working paper that I put the QR code for. and it's in the chat. So indeed, one of the applications is to value the default option that a counterparty has when they're supposed to post collateral, and just once they cannot do it, right? And so I set all the floors to 0 for that application, because I'm thinking that if they don't post collateral, you as the counterparty are getting 0 instead of the collateral. But if if instead you were getting some other amount, like, you could take over their company and get whatever they're worth, and that's a known amount, yeah, then you could use other floors than 0. So indeed, so thinking about the, it goes back to Merton and the Black-Scholes paper that, the ability to default is an option, and they were thinking only about defaulting at maturity. In reality, people default potentially earlier than maturity by not posting collateral, and this is indeed the right financial structure to think about that possibility. So actually, it was a guy at Morgan Stanley, where I used to work, who wrote me about how to think about collateral posting that got me to think about this. So I'm agreeing that this exists in practice. Actually, in the abstract in my talk here, I mentioned DVA, which is the, DVA, debit valuation adjustment, is the term for the value a person has from the ability to default. Okay, so if you're the person who's supposed to post collateral and you choose not to, then that has value to you, and one can use the stoption formula to capture that value. Anil, do you have your picture's there. Do you have a comment?
Anyone else?
Okay,
Sir, I have a question, sir.
go ahead.
Go ahead.
Sir, are these stop options, can they be used in globally? Like, I'm from India, so can